Hi, good morning all to the AI Summit. Welcome to the AI Summit 2021, Day 2. Yesterday, we had exciting keynotes, panel discussions, and product demos as well. Today, it's the second day, starting with exciting keynote on AML security from an eminent personality in semiconductor, Dr. Walden C. Rhines. Let me introduce him. He's the president and CEO of Emeritus and Konami Incorporation, a fabless semiconductor company focused on intelligent computing. Dr. Rhines was the former CEO of Mentor Graphics for 2.5 decades and chairman of the board for 17 years. During his tenure, market value of the company has increased to 10x. Prior to Mentor Graphics, he was an executive vice president of Semiconductor Group, responsible for TI's worldwide semiconductor business. Also served as several boards in various capacities. And he was the chairman of Electronic Design Automation Consortium. For a decade, he has completed 5 two-year terms. He's a lifetime fellow of IEEE. Dr. Rhines holds a bachelor degree of science in engineering from University of Michigan, Master of Science and PhD in Material Science and Engineering from Stanford University, and Master of Business Administration from Southern Methodist University, and Honorary Doctor of Technology degrees from the University of Florida, Nottingham Trent University. It is a warm welcome to you, sir, to address the delegates of this morning.
Thank you, Satish. Hey, I hope my friend Satya Gupta is in the audience here today, because I want to talk about AI as it applies to data. So let me go to my slides. Let me see, right here, yeah. A moment. And talk about how big data drives really a new era for artificial intelligence. So think about artificial intelligence back over the last 35 years. Let me take you back to High Technology Magazine. This is the cover 35 years ago. And it says, artificial intelligence, heavyweights get into the act. Now, I know it's hard to recognize me with that much hair, but that's me in the picture. And this is George Halmeyer, who was the head of DARPA, the Defense Advanced Research Projects Agency. And we were in the business of artificial intelligence. But you know, there wasn't much business. And there are a lot of reasons. There was a lack of big data to analyze. We didn't have an Internet of Things. There was limited computing power. There was a need for more advanced algorithms. And really, the biggest thing was there was a lack of killer applications to make money. One by one, these limitations have disappeared. So today, new applications are driving a lot of momentum, and it applies to the semiconductor industry as well, because the semiconductor industry is driven by applications. Every major wave of growth in the semiconductor industry comes with an application. Mainframe computers, standalone PCs, notebook PCs, mobile communications. I think the latest one could be grouped together as data. Well, people talk about a lot of other things. They don't just talk about data. They talk about the role of artificial intelligence, machine learning, IoT, 5G communications. But you know, all of these things have one common factor, and that's the fact that they're being impacted by the effects of large volumes of data. We're building machine learning models with AI. IoT is bringing computation closer to the point of data collection, and 5G is dealing with real-time communications for factory automation and autonomous drive vehicles and other things. So while artificial intelligence is not new, what is new is the fact that the quantity of data to be processed is very new. Data, as many have said, is the new oil. It contains all of our experience, our know-how, our insights into what we deal with every day, and it gives us a basis for analyzing the way the world works and predicting how things might evolve in the future. Quite a while ago, I looked at the business of aircraft manufacturers who made engines for airplanes. Pratt & Whitney, General Electric, Rolls-Royce, companies that make those engines, monitor them all the time. So it doesn't matter what airline you're flying on, the fact is they're monitoring the behavior of the engine. And it's a lot of data that they produce. In a 12-hour flight, 844 terabytes of data. All that data is collected to do predictive maintenance analysis and to determine, are there any problems? And so the manufacturer of that engine, regardless of who is using it, has a monopoly on the behavior of that engine. So aircraft engine manufacturers could give away the engines for free and just charge for the support and the maintenance because you can't afford to fly your airplane without it. Well, today, I want to talk about three aspects of data and how we're making it the new oil, the store of wealth: the collection, the analysis, and the protection of that data. Let's start with the collection. We're collecting a lot more data than we can analyze. By some estimates, we only analyze about 2% of the data we collect. That's been accelerated to petabytes per day with video data, surveillance monitoring, all the video we take for all the things going on, and related information for a variety of applications, image processing and other things. But sensors everywhere are collecting a lot of data. And you know, for the semiconductor industry, that's been a challenge, developing sensors that can collect that data. After all, you have to have a sensor. Maybe it's a different technology like MEMS or a thermal sensor. And then you have to be able to convert the analog to digital. And then you have to do some sort of memory store and possibly local analysis of that data. And then you have to transmit it through a serial link, through RF communications. That's very tough for design engineers because you're combining multiple technologies together, and to simulate a module like that is quite difficult. So you would think that the semiconductor industry was raking in lots of money developing these things. But in fact, they're not. They're at the bottom of the food chain. The people who develop the sensors and the engineered package solutions don't collect very much money. It's the people who collect the information, they analyze it, and they use it, and they sell the results back to you. Well, about 5 years ago, I was attending a design automation conference presentation by some engineers at Google, and they were showing how they had developed a chip to be embedded in a contact lens that would sense in the liquid of your eye the balance between glycogen and insulin, and therefore be able to control an insulin pump you would carry on your body through your iPhone or through your cellular phone or whatever. And the person next to me turned to me and said, "Oh my gosh, Google is getting in the semiconductor business." And I thought about it, said, you know, Google's not getting in the semiconductor business. The semiconductor business is not that good a business. They're in the information business, collecting the information from you, being the interface to your doctor, being the organization that can help you use that information to provide better health for over 380 million people. Well, that's spread. Systems companies everywhere have jumped into the game of designing leading edge chips. And that's what's propelling the growth of the EDA industry from what used to be a 3 to 5% per year growth rate to now a 9 or 10% per year growth rate. It's the Googles and Facebooks and Amazons and Alibabas and others, but it's also the automotive companies, the OEMs and the tier ones. All these people are designing chips and collecting data. Tesla impressed everyone with a very impressive AI chip for machine learning, customized specifically for the operations required in operating a car. If you look at who's buying the foundry wafers today, go back 10 years, and basically it was fabless semiconductor companies for most of the business, and then integrated device manufacturers, Samsung, TI, Intel, and others for the rest. almost no systems companies, no Apple computers, no Alibabas, Facebooks, Amazons. Look at it now. Almost 20% of those wafer purchases are from systems companies who are in fact becoming their own semiconductor suppliers, designing their own chips and using them for differentiated value. Well, let's look at the analysis. Domain-specific processors have emerged that handle large amounts of data and allow us to analyze it and gain insights. Now, traditional computers are von Neumann architectures. They have memory and they have operations, and they take something from memory and they operate on it and they put it back into memory. That's the way computers have operated for 70 years. But it's not very efficient for a lot of the operations we're talking about in artificial intelligence. Good example is pattern recognition. And the other thing is, while your brain is orders of magnitude more efficient in recognizing a pattern, or you pick up the phone and in milliseconds you can tell who's talking on the other end of the line, your brain does it very well. Digital computers don't. But what's more important is the use of power. 9 orders of magnitude between the difference of how much power your brain consumes versus what a typical chip consumes, performing the same pattern recognition. So we're attacking that. We're putting neural networks on chip, and these neural networks are growing in the number of layers. And as they grow in layers, they grow in intelligence. And we build in information through training, and we build coefficients that are then part of the intelligence base of that neural network. And that increasingly is building massive stores of intelligence information that we can use by inference to gain conclusions of the information we've stored. You know, this has not missed the semiconductor industry. We had, in the year 2000, a peak in venture capital funding of semiconductor startups. It went to about $2.5 billion, and then it went into decline. It was no longer fashionable to invest in fabless semiconductor startups, and so the investments dropped to below $500 million a year. And then in the year 2017, all of a sudden it took off to 1.6 billion, and then to a new record at $3.5 billion in 2018, and it stayed around $2 billion per year, because we need new architectures to analyze the data that we're generating and that we need to use artificial intelligence to analyze. Well, where are those designs being applied? Well, most of them are for artificial intelligence and machine learning. Of those total number of dollars between 2012 and 2019, most of them went into designing chips that were non-conventional architectures. And what were the applications that they were targeting? Well, I've collected them here and just added them up numerically. The largest category is pattern recognition, and that covers a lot of things. Of course, visual and facial recognition is the largest part of it, but it includes other things. For example, voice and speech recognition, and the disease diagnosis, analyzing an MRI or an X-ray, which computers can do much more reliably than humans, and a variety of other things, including autonomous drive. Good example, SenseTime, about to go public this year. It has a valuation of over $12 billion, $1.6 billion of investment in venture capital. They're doing their final round before going public. Enormous amounts of money, but then again, China has over 1 billion people where facial recognition is very important. The second largest category, the data center, high performance computing, the cloud AI, an area where really NVIDIA has dominated with the parallelism that exists in graphical processors. But there are new architectures coming along. The TensorFlow processors from Google are a good example, where they have servers in their data centers that can do specialized machine learning and provide unique computational capabilities. The TensorFlow processors, and now a host of others, including those from my own company, Kornami, that can perform the analysis of data and building of machine learning models at orders of magnitude faster than traditional computers. The third category, edge computing. Putting those chips out in the world, in the edge, in cars and trains and planes and other places. That's one that has yet to evolve, but will be enormous. So how do I know that'll be enormous? Well, the fact is I know from history, because intelligence flows downhill over time. Go back to the 1960s, and we had mainframe computers attached to dumb terminals. 20 years later, the mini computers stepped into that hierarchy and did the local consolidation and processing of data. Another 20 years, and the personal computer was taking care of a lot of local processing. So the intelligence had moved downhill from mainframes down to the individual. And today, large servers in the cloud, and then gateways in what might be referred to as the fog, and edge nodes at the mist. The intelligence continues to migrate downward until eventually the chips that we deal with locally have enormous amounts of compute power to do the machine learning and the data analysis. Well, the third thing, and the one I find most exciting, is the protection of data, and it's becoming the big issue. So there are three approaches that have been identified for how to share the value of data. If you've got a valuable set of data, you can bring your data to the algorithm, and you can trust the data center, and you can put your data in the data center and let other people access it. You have to trust Intel, ARM, Dell. You have to trust anyone who has access to that data. And so it's not a very secure environment. Google popularized the concept called federated learning, where you put your machine learning model in the cloud, but then you download a portion of it to somebody's personal computer or cell phone, and the model learns from them and then is sent back to the cloud. Once again, there's a lot of trust required by you, if you own the data, that that downloaded model won't steal your data in a way you didn't authorize, and that the others who are exposed to your data won't take advantage of it without paying you for the benefit. There's only one way where you have to trust no one, and that's homomorphic encryption. Trusting no one, you keep the data encrypted at all times. So how's that work? Well, you as the client encrypt your data, and then you send it to the cloud, still encrypted. No one has the key. All the information is processed in the cloud, and then the encrypted data results are sent back. No one ever sees the plain text. No one can ever see your data. DARPA has characterized this as the holy grail of computer security. What is that holy grail? Well, fully homomorphic encryption provides what's called quantum secure encryption. It can't be hacked. It enables all types of arithmetic and logical computation to be performed while keeping the data encrypted. It's really critical for financial, medical, military applications and other things. So you're preserving the privacy of the training data. That is, nobody can go into your model and figure out the source of your data. The input privacy guarantees that you can take data that's encrypted and protect it while you're building your model. The output, it remains encrypted, and the model itself remains encrypted. Well, machine learning using encrypted data creates a new era. So you can build a machine learning model where you own the data and no one ever sees it. They simply pay you for the use of the data. You can make encrypted queries to encrypted models that were built using encrypted data and return the results still encrypted. That's really critical. It's going to be a very large market. Well, machine learning using encrypted data ought to be the way we do everything today. But there's a reason that we don't. And that's because it requires enormous computational power. Let me show you how much. A single bit of data coming into a logical AND gate is converted into a 500-order polynomial with double precision floating point coefficients, and then to do the calculation of the result requires 3,000 1,000-point complex floating point, 64-bit floating point fast Fourier transforms, enormous computation. If you try to do that on a standard processor with multi-core, you'll get some acceleration as you use a few more cores, but you get more than 5 cores, and the thrashing of data, the sharing of memory doesn't work on von Neumann computers. What does work is if you have a compiler that can compile things into independent threads that run on the cores of a computer and where you can get linear scaling. That's the solution. That's the way we're going to move forward. We had an example at our company where a customer came in that wanted to implement fully homomorphic encryption. They had run it on 24,000 Intel cores, 12 and a half racks of equipment. It took 4.4 days. But if you do it on a configurable multi-core parallel processor, you can do that in 10 seconds. The world is opening up to fully homomorphic encryption. The key requirements to get that million X performance: massive parallelism at the same clock rates, minimizing memory reads and writes. That's where most of the power dissipation occurs. Software compilers that can generate independent executable streams of data and control, and chip hardware that scales linearly across chips, across boards, and across servers. There are a lot of factors driving fully homomorphic encryption, but if you go and look, you'll see companies like IBM and Intel and AT&T and others highlighting their move to fully homomorphic encryption to secure the data instead of the data center. There are regulatory issues because data breaches are costing trillions of dollars. Microsoft already has a product called Election Guard that was used in the 2020 elections with partially homomorphic encryption. The Department of Defense in the US is committed to converting, and hundreds of companies already have homomorphic encryption programs, and Gartner predicts that 25% of all companies will have it by 2025. A very large market in the next few years, and a lot of companies helping companies to convert. You talk about the sword of Damocles, that is the impending doom. We have impending doom. Quantum computers can break most of the security on the internet whenever they get to 1,000 qubits or greater. And that's going to happen over the next 5 years or so. Fortunately, we have fully homomorphic encryption that can replace all the current security and can move us forward without fear. And that's why you're seeing so much publicity, so many companies talking about it. The world is going to be one of fully homomorphic encryption. It's going to be very important. So those are the 3 elements. Making data the new oil requires efficient collection, analysis, and protection of data. And with that, we'll move into a new era of artificial intelligence and machine learning that allows people to collect that information and market it to other people who can gain value from it, can use it, but they never see it. It remains encrypted, and so the owners can continue to profit from it, and it'll create an enormous business in the future. So thank you. And with that, let me take any questions you have.
Dr. Rhines, we have a question from audience. Will there be a packet loss with such high volume of data transfer in TPU-based cloud or data centers, please?
I'm sorry, I didn't quite hear all that.
Yeah, will there be a packet loss?
Oh, a packet loss. I'm sorry. No, because the data is encrypted at the site of the client. So whatever you want to protect, you encrypt. Then it is protected in transmission, it's protected in processing, and it's protected in transmission of the results back to you. And so in terms of the efficiency with dropping packets or other things, it's all ones and zeros once you've encrypted it. So no more risky than packet loss in current transmission.
Yeah, we have one more question. How does the future looks like?
So I believe this is going to be revolutionary. I think you will see co-processors in every data center. Eventually, you may see incorporation of fully homomorphic encryption in all processors, but we cannot live with the level of data security we have today. We cannot trust the data centers. We cannot trust the operating systems. We can't trust the chips. We have to secure the data. So every organization that deals with confidential data needs to be able to encrypt that data. So I believe you will see over the next 5 years, people will move to fully homomorphic encryption so that the data is never revealed, never decrypted, and is always secure. And you can be confident that those who have your data are not going to reveal it to anyone else.
Yeah, thank you so much. And you have given a deep insights. And it is really pleasure to have the eminent speakers like you in this panel. Thanks a lot. Thanks once again.
Thank you, Satish. A pleasure to participate.
Thank you. Thank you.
Thanks.
Yeah.